Welcome to day 11. We're going to look at vector valued functions today. So first couple on the homework, we wanted to write it in component form. So when you go from 1, 3 to 5, 6, that's 4 to the right and 3 up. So you have 4, 3 for your vector. 2, you went 6 to the left and 1 down, so -6, -1. And then -5.1, 31, 6. Could also have that as -11 halves for the first part. In 4, just multiply vector u, both parts by 3/4. In 5, multiply w by 2. Distribute the -1 through u and then combine, you get -311. And you can either multiply the -5 and -3 first, or distribute the 1/2 and think of it as multiplying by -5 halves and -3 halves, but in the end you get -14 3/2. 7 through 9, you had to set up a system of equations. So essentially, think of this as 1a and 2a, and this is 1b and -1b. So the first part of the component, the x component, we've got 2 is equal to a 1a. Oops, I made a mistake here. This should be 1b, sorry. 1a plus 1b. And then the y part 1 should be equal to 2a minus 1b. You can do a little elimination there. You end up getting a is 1, is b is 1. And then you do a similar idea for each of the others. Our magnitude, we got the square root of the x part plus the x part squared plus the y part squared, so we get a magnitude of square root of 13. In 11, add them together first. You get 6, 1 for your vector, and then take the magnitude. You get square root of 37. In 12, do the magnitude of v, which is what I did over here, and got 4 square root of 2. Then you're doing your vector v divided by that, so that gives you a vector of 1 over square root of 2 for both parts. And then when you do that magnitude, square root, square them and add them, we end up just getting 1 in the end. For 13, add u and v we had from before was 6, 1. We also had u plus v's magnitude from question 11, square root of 37. So put those both over square root of 37, then do the magnitude, and you end up getting 1 as well for that one. Here you have arctan of 4 over 4, so that's the same as arctan of 1, which is 45 degrees. For this one here, you would have arctan of 3 over 2. Add them together, you get 101.310 degrees. So note, this is like the one place where we do degrees in calculus. So if u has a magnitude of 1 and theta is 0, the component form has to be 1, 0. If v has a magnitude of 4, and we have 45 degrees, well, these should be the same. So you can think of them as our initial 45, 45, 90. We have square root of 2, 1, and 1. Square root of 2 would have had to have been multiplied by 2 square root of 2 to give you 4. So multiply these by 2 square root of 2 as well. So that's where you get your component form for v. And then we wanted to find u plus v, so add them together. You get 1 plus 2 square root of 2, 2 square root of 2. In 16, we have a 30-degree reference angle. So normally we would have 2 here, so that means we multiplied everything by 5 halves to end up with 5. So across from the 30 you have 5 halves, across from the 60 you have 5 halves, radical 3. So then you get your vector for u, 5 radical 3 over 2, 5 halves. And then we have a 60-degree reference angle for the other one. That's just our base triangle, because you have a hypotenuse of 2. So your x part is -1, y part square root of 3. Add those together to get the sum vector down below. So we're going 125 straight ahead, and then 75 pounds right of center. So imagine you are looking to the right, because that's your straight ahead. So right of center would then be down and to the right 15 degrees. Draw in your resultant vector. And then this part would have to be the same as the 75. We can do, because that was 15, we know that this one would have to be 165 because they're supplementary. Then you can do a law of cosines to get the magnitude of the resultant force, which is that 198.396 pounds. And then do a law of sines there to get the degree value. So that's the one way you could do it. The other way you could do it is work with this kind of triangle here. Or actually, probably the other one is the better one to work with, this type of triangle here. So if that was 15 degrees, this part here would be 75 times cos 15. This part here would be 75 sine 15. You could write the resultant then as a vector and then do the magnitude, and then just do your arctan of the y over the x part to get the angle. So either one of those, it's just your preference. In 18, we are going 8 to the north, and 18, or sorry, the current was 8 directly north, and we were traveling 18 knots northeast. So our true path of the ship is this one here. So if that's 18, you can write the component form of the vector as 9 radical 2, 9 radical 2, because that should be a 45, 45, 90 triangle. And then the resultant component, we would have to add the 8 onto the y part. You can then just do your magnitude calculation to get the speed that the ship is going. And then to find this angle here, this part here would be the 8 plus 9 square root of 2, and this would be 9 square root of 2. So you do arctan of your opposite over your adjacent, and you get 31.552 degrees, and that is east of north. These ones were from earlier in the unit. Do the derivative of the y part over derivative of the x part. When you sub in 0, you get 2/3. For the second derivative, do the derivative with respect to t of the first part, which gives us this, and then you always have to do it over dx dt. Neaten that up, sub in 0, we get negative 4/27, so we are concave down. Similar idea for this one, derivative of the y part over derivative of the x part. It neatens up to be 2 cosecant theta. Cosecant at pi over 6 would be hypotenuse over opposite, so that's 2 over 1, so you end up getting 4 for the slope. Do your derivative of 2 cosecant, which is this, over the dx dt, which is that. And then I wrote them all in terms of sines and cosines. Here's our cosecant, here's our cotangent. And if you're dividing by secant, you're multiplying by its reciprocal. If you're dividing by tan, you're multiplying by its reciprocal. You end up getting negative 2 cotangent cubed. Pi over 6 cotangent is square root of 3 over 1. So when you cube that, you end up getting a negative, so it's concave down. So we're going to be day 11 in your notes packets. We're going to look at vector valued functions today. And what a vector valued function is the x part and the y part are in terms of a parameter t. So at each value of t, we are given a vector. The tip of that vector is then plotted as a point. Well, you do that for all values of t, and basically this curve here is where all the different tips of the vectors would be located. We would then need to put arrows on it to show the direction it's going. So they're telling us here, R0 for us is 0, 1. So that's where this point is coming from. To figure out what our arrows will do, we'll pick some other points. So let's pick something that's negative. So maybe like R of negative 4. Negative 4 squared is 16, and then we'll have e to the negative 4. So we're just getting that from putting it in here. So 16 negative 4 is going to be something over here. So then our zeros after that, so that tells us our direction is actually going this way. And that allows us to put our arrows on. So if you have the initial, pick some other one either before or after it, and that'll help you tell the direction it's going. Now your domain of a vector valued function is the intersection of the domains of each of your parts. Well, a quadratic is all real numbers, an exponential is all real numbers, so therefore this one would be all real numbers as well. If we go down to the bottom, if we want the domain of this vector valued function, well, let's look at the domains of the parts. When you have a radical, we need it to be positive or 0. So that means we would want to make t minus 1 greater than or equal to 0. So we get t greater than or equal to 1. We'll do a similar idea here. We need 5 minus t to be greater than or equal to 0. If we add the t over, that means we need t to be less than or equal to 5. So if we think of this on a number line, here's 1, here's 5. We need t to be greater than or equal to 1. So that graph would look something like that. We also need t to be less than or equal to 5. So our domain of the vector valued function is just the intersection of those. So we would have 1 less than or equal to t, less than or equal to 5, is where the values of t that would work for our vector valued function. So we've got another vector valued function here. So again, the graph we would get would be the tips of all the possible vectors that would come from subbing in different values of t. So we're going to start with we're going to do our nice values of t. So if we sub in 0, cos of 0 is 1, 1 times 2 is 2. So for the first part we'll have 2, sine of 0 is 0. So we'll start by plotting 2 comma 0. If we put in pi over 2, cos of pi over 2 is 0. Sine of pi over 2 is 1 times the negative 3 gives us negative 3. So our next point will be 0, negative 3. So keep that in mind. We went for that point on the right and then down because that's going to tell us the direction eventually. If we put in pi, cos of pi is negative 1 times 2 is negative 2. Sine of pi is 0. So next we'll have negative 2 comma 0. 3 pi over 2, cos is 0. Sine is negative 1, so when you do times the negative 3, that gives us positive 3. And our last one, when we put in 2 pi, cos of 2 pi is just 1, so we're back at 2. Sine of 2 pi is 0. So we started here, and we went around this way. So our arrows should go like that. Now I scaled mine kind of poorly, but this should be an ellipse, because in the horizontal direction we have a radius of 2, in the vertical direction we have a radius of 3. Now how you could see that it is an ellipse, so if we took that 2 cos t and set it equal to x, that means cos t is x over 2. And if we took that negative 3 sine t and set it equal to y, that means sine t is negative y over 3. Well then, eliminating our parameter, we know that we have sine squared t plus cos squared t is equal to 1. So if we square our sine part, we'll get y squared over 9. If we square our cos part, we'll get x squared over 4, and that's equal to 1. And this is our form of a ellipse. Our radii are the square roots of those denominators, so we have 3 radius in the y direction, 2 for the radius in the x direction. So with vector valued functions, you can do limits. On the right there, we have a graph of this vector valued function. If you're doing the limit of the whole vector valued function, all you do is the limits of the individual parts. So this we would rewrite as the limit as t approaches 0 of sine t over t, comma, limit t approaches 0, t squared plus 2t over t. Well, this first one is a limit that we've seen a lot. That's just 1. This second one, we can divide a t out of everything. So we can rewrite this as t approaches 0. It'll just be t plus 2. And now we can evaluate that limit with direct substitution. So this will just be 1 comma 2, and that will be our limit. Now we could have, from this graph, we could have noticed that visually, but you won't always have that graph to look at. That's how you would do it algebraically. So we looked at domains. The domain was the intersection of the domains of the parts. Now we have continuity. So vector valued functions similarly are just continuous where both parts are continuous. So natural log, its graph looks like this. So it is continuous when t is greater than 0. 6 minus t, it's continuous on its domain. So we need 6 minus t to be greater than or equal to 0. If we add the t over, that's when t is less than or equal to 6. So we need to be greater than 0, but less than or equal to 6. So therefore, we are continuous, 0 less than t, less than or equal to 6. In our second one, tan has asymptotes. Tan has asymptotes at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. So tan is continuous for all real numbers. T, not x. T cannot equal n pi over 2, where n is an odd integer. And this one is all real numbers because it's a quadratic. So for where this is continuous, you could either say it like this, that would be fine, or you could write it as an interval. You could say n pi over 2, comma. If we were, say, at like 1 pi over 2, we would want to jump 2 pi over 2's to the next one to 3 pi over 2. So we would say n plus 2 pi over 2. Where n is an odd integer. So maybe this is 1 pi over 2 and 3 pi over 2. On that interval, it's continuous. 3 pi over 2, 5 pi over 2. On that interval, it is continuous. So that represents all those intervals in continuity, or you could write it, the all real numbers, just t is not equal to n pi over 2, as long as n is an odd integer. That's it for this video. Have a great rest of your day.